let's focus now on power functions. Power functions are functions of the form f of x equals x to the n, where here n is going to vary and will be sometimes any positive real number, sometimes n is a negative real number, sometimes n is just limited to whole numbers. But the point is that the function is a power with base x and exponent n. So what is the end behavior of power functions? In fact, their end behaviors are quite simple, and that's because power functions are a special case of polynomials. And I know that you studied polynomials quite a bit in pre-calculus, so hopefully this will be very straightforward for you. So here is a simple power function, x to the fourth, and even x squared right here. X squared is the pink function, x to the fourth is the blue function. And you can really see that in both cases, the end behavior at positive infinity and the end behavior at negative infinity is the same. The end behavior in both cases is positive infinity. When we look at power functions with odd exponents, x to the fifth, x to the third, the end behavior is slightly different. As x approaches positive infinity, the end behavior is positive infinity. And as x approaches negative infinity, the end behavior is negative infinity. And when we consider rational functions, 1 over x, this is like considering x to the negative 1. All of a sudden, we let n be a negative real number. You really notice that the end behavior is quite interesting. In these two cases over here, actually 4 cases, 1, 2, 3, 4, we never got horizontal asymptotes because we always got infinite limits. However, when you look at this graph 1 over x, or simply x to the negative 1, you notice that the limit as x approaches positive infinity is finite, is 0. And in this case over here, the limit as x approaches negative infinity is finite as well, 0. So all of a sudden, that makes the x-axis a horizontal asymptote. And this is a typical behavior of power functions with negative exponents. So this is what I want us to do right here under case 1 and case 2. I want us now to describe power functions in general. I want to have general statements about power functions. So case 1. If n is any real number greater than 0. So right here, n is greater than 0. So like in this case over here, n, the exponent can be 4, can be 2. The exponent can be even 1/2, 1/3, 7 over 5, any real number bigger than 0. I am not saying that n has to be a whole number, any real number. So if that is the case, the limit as x approaches positive infinity of x to the n is going to be equal to positive infinity. And the limit as x approaches positive infinity of 1 over x to the n is going to be equal to 0. And I'm hoping that you can see that nicely. As x is getting very, very large positively, x to the n is getting very, very large. So then that means that 1 over x to the n is going to get very, very small. So it's going to become 0. So now you know, from now on, if you ever encounter, for example, the limit as x approaches positive infinity of x to the 7 over 3, I want you to think about the exponent. 7 over 3 is a real number bigger than 0. So according to this result, this should be equal to positive infinity. And if you encounter something like the limit as x approaches positive infinity of x to the negative 7 over 3, don't let that pretty much scare you away or something. You know that you can rewrite that negative exponent as 1 over x to the 7 over 3. And now you do have a power with a positive exponent. So then you know this result right here. You know that this limit is going to end up being 0. Case number 2. What happens if n is a whole number? We're going to go ahead and simplify matters here by considering only exponents that are whole numbers. And the reason is because I want to consider now limits at negative infinity. And if the exponent of the variable happens to be 1/2, and let's say I consider negative 2 to the 1/2, then I know that this will be undefined as a value of the function. So in order to avoid undefined scenarios, let's just right now consider this condition where the exponent is a beautiful whole number. So if we do that, that means that n could be even. So what happens if n is even? If n is even, then the limit as x approaches positive and negative infinity of x to the n will be equal to positive infinity. And this is simple right here. This case here is demonstrated in the first graph. Look at these U-shaped graphs. X squared, x to the 4th. In both cases, at positive infinity and negative infinity, the y values go off to positive infinity. That's what I'm trying to say here. Now, what happens when n is odd? So if n is odd, now we have an odd exponent. If that happens, then the limit as x approaches positive infinity of x to the n will be equal to positive infinity. And the limit as x approaches negative infinity of x to the n will be equal to negative infinity. That is always the case. And you can see that right here. This is a great demonstration of this case. Here we have x to the 3rd, x to the 5th. And as x approaches positive infinity, look at the y values in both cases, positive infinity. And as x approaches negative infinity, the y values go off towards negative infinity. Now let's do the reciprocal of these functions. So in this case over here, right here, the limit as x approaches positive and negative infinity of 1 over x to the n is going to be 0. Again, hopefully you can see that easily. As x to the n gets very, very large, because of this case above right here, 1 over x to the n gets very, very small. And in this case right here, same idea. The limit as x approaches positive or negative infinity of 1 over x to the n will be equal to 0. Now, you can try to memorize these rules over here, but I'm going to say don't. Just think of the graphs. You can reach the same conclusions just by thinking of the graphs of power functions, just by focusing on the nature of the exponent. Is the exponent even? Is it odd? What is, even if it's 7 over 2, 7 over 2 is 3.5, then that means that as x goes to positive infinity, x to the 3.5 is getting very, very large and stuff like that. So just think of the graphs. That's why you spent so much time in pre-calculus last year studying behavior of polynomials, the end behavior of polynomials, so that you can now in calculus use that knowledge easily to determine end behavior. So that will be my advice instead of trying to memorize these rules. Let's go over these examples. Example 1. Example 1 is asking us to evaluate the following limits. Part A, the limit as x goes to positive infinity of 3 minus 4x to the negative 3 plus 5x to the negative 5th. So here I'm going to use a combination of things. I am going to use my knowledge of power functions because I can think of every single term as a power function. This is an addition and subtraction of power functions. And I am going to use my limit laws. Because I have addition and subtraction, my limit laws says that if the limits of the individual terms exist, I can apply the limit to each term individually. So I will take advantage of that and I will do exactly that. So this will be equal to the limit as x approaches positive infinity of 3 minus 4 times the limit as x approaches positive infinity of x to the negative 3 plus 5 times the limit as x approaches positive infinity of x to the negative 5th. This first limit right here is the limit of a constant. That is just equal to 3. This other limit right here, I'm going to go ahead and rewrite the power function as 1 over x to the third. I will turn the exponent positive. And here, same thing. The 5 times the limit as x approaches positive infinity of 1 over x to the 5th. Now, I am going to use my knowledge of limits at infinity of power functions. The limit as x goes to positive infinity of 1 over x to the third. You can try to remember the rules, but think about it intuitively. Think of the graph of x to the third. As x gets very, very large, incredibly large, x becomes 1,000, 10,000, 1,000,000. X to the third is growing even faster, is getting even larger. So 1 over something very, very large is going to be very, very small. So this limit is going to go to 0. That means that I have 3 minus 4 times 0. This limit right here is going to be 0. And then over here, plus 5 times, and again, same idea. As x gets very, very large, x to the 5th gets even larger. So 1 over x to the 5th is going to become 0. So then the value will be 3 minus 0 plus 0, 3 is the value of that limit. In part B, I will do something very similar. I have a quotient, but I know that the limit of each of these functions exists. Same thing over here. So, according to my limit laws for limits at infinity, I can apply the limit to the numerator and to the denominator. So this will be equal to the limit as x approaches positive infinity of 3x to the negative 2 minus x to the negative 1 minus 2. All this, actually, should be all this divided by the limit as x approaches positive infinity of 4x to the negative 4 plus 1. Then my limit loss says that I can apply the limit to each term separately. So then this will be equal to the limit as x approaches positive infinity. I'm going to put the numerical coefficient in front of the limit, and even immediately I will change the negative exponent to positive exponent just to save a little bit of energy writing this out. And then here minus the limit as x approaches positive infinity of 1 over x minus the limit as x approaches positive infinity of 2. All this will be divided by 4 times the limit as x approaches positive infinity of 1 over x to the 4th plus the limit as x approaches positive infinity of 1. So in the first case, this limit right here is going to go to 0. This limit is going to go to 0 as well. And this limit is a constant, so we're just going to get 2. So here we're going to have 3 times 0 minus 0 minus 2. All this divided by 4 times 0. Again, because as x goes to infinity, x to the 4th is going to infinity. So 1 over something very large will give us something very, very small. So 0. And over here, plus 1. So then that means 0 minus 0 minus 2 over 0 plus 1. That will be negative 2 over 1. Negative 2 is the value of that limit. Let's consider the last example. The limit as x approaches positive or negative infinity of x squared plus 3x to the negative 2 over 2x to the negative 1 plus 4. I want you to right away look at these limits, and hopefully by now you're starting to see, or you're starting to recognize the values of the limits at infinity of the power functions. So in this case, we have x squared. X squared goes towards positive infinity. And then this one goes to 0. So the numerator, let me just do the numerator. I'm going to do the numerator here on the side. I have here the limit as x approaches positive or negative infinity of x squared plus 3x to the negative 2. So what I just said over here is that the limit of the first term is going to go to infinity, and then the other limit is going to go to 0. And infinity plus 0 is not an indeterminate. It is actually equal to infinity. In the denominator, the limit at infinity of the first power term is 0. And the limit at infinity of 4 is just going to be 4. So the limit in the denominator is equal to 4. So I would write here that the limit as x approaches positive or negative infinity of 2x to the negative 1 plus 4 is going to be equal to 4. So this is where we're going to use part 6 of the limit laws that we just discussed a while ago. Even though the limit of the numerator is infinite, I have an infinite limit at infinity, and the limit of the denominator is finite. Number 6 of the limit laws says that I can apply the limit to the numerator and denominator, and I'm going to get a result. So in this case, I'm going to tackle the problem like this. I can have the limit as x approaches positive or negative infinity of x squared plus 3x to the negative 2. That is going to be equal to the limit as x approaches positive or negative infinity of 2x to the negative 1 plus 4. So limit law number 6 allows us to take the limit and apply it to the top, and take the limit and apply it to the bottom. That's what I'm doing over here. And then by this discussion right here, I already know that the limit in the numerator will be equal to the limit as x approaches positive or negative infinity of x squared plus 3 times the limit as x approaches positive or negative infinity of x to the negative 2. Actually, I can even write this as 1 over x squared, and that will be divided by the limit as x approaches positive or negative infinity of 1 over x, and allow me to write the coefficient in front of the limit, plus the limit as x approaches positive or negative infinity of 4. In the numerator, based on what we discussed from here, we know that the limit on top is going to be infinity plus 0, which is infinity, divided by 2 times 0 plus 4. So that will be infinity divided by 4. That is going to be equal to infinity. So then we discovered that this limit at infinity is an infinite limit as well.